Yeah, so thank you for the organizers for inviting me to this conference. To be honest, I don't do that much with Gapless stuff, but this is an interesting, simple toy model that I've been studying with Rahul and Ruben, and it displays some gaplessness. We call this the funky ising model. Okay. So the punchline of the story is that in certain kinds of quantum states, you can get an incompatibility of order and disorder parameters. And when you have that, then it seems like when the incompatibility means that it's incompatible with any gap state that we know, that seems to lead to gapless parent Hamiltonian, or it could lead to extra spontaneous symmetry breaking, but the particular model that we have seems to have gaplessness. And this is interesting because you can have this incompatibility even when this ground state has exponentially decaying connected correlation functions and parameter law entanglement, so it looks as gapped as it can possibly be, except for this particular correlation. And so the gapless parent Hamiltonian that we find has kind of z equals 2 gaplessness, and it has, we can somewhat characterize its low energy excitations, which are these kinds of loop wave, which I will show later in the talk. And as I will show, this requiring certain properties of the order and disorder parameters leads you to conclusions that sound similar to when there's an anomaly of the symmetry. But there is none, and it's just because we require certain correlation functions to be certain long range. Okay, so this is the very, very simple toy model. It has occurred in many different contexts, which I will mention in the next couple slides. And it's just a product of e to the beta over 2 zz on the all plus state. So then it has a bunch of these nearest neighbor couplings, and it's appropriately normalized. And you can write a local parent Hamiltonian for this simple model. You can show that this Hamiltonian is, oh, I do? Okay. This local Hamiltonian is positive semi-definite, and it annihilates this state. So this is the ground state of this local Hamiltonian. And this looks like it's a 5-body term, but it's actually a 2-body term if you expand this in Sinch and Koch. So it's a very simple local Hamiltonian, and its ground state is this very simple state. And we can look at, we can find this state in many different contexts. So this was initially studied in the context of Rockstar-Kivelson models, which are models where you have a quantum ground state that is like a 2 plus 0D classical partition function. And it's also studied in the context of conformal quantum criticality by this paper and many others, if you tune this to, say, its critical point of the classical model. It's also studied in the context of tensor networks because it's an example of a so-called weakly non-injective tensor network in 2 plus 1D. And then its entanglement properties, the dual like toric code type model was studied, and its entanglement properties were studied in this paper, and then several subsequent works. And this kind of model has also popped up more recently in the context of density matrices and the study of density matrices. For example, if you take toric code and you decohere it, and you look at the choice state, then you get something like this. So, so this is a model that looks kind of fine-tuned, but it pops up in many different contexts. Okay, so in the limiting cases, you can obviously see that beta goes to 0, you just get a paramagnet. And you can expand this for small beta, so it's just a paramagnet with some small perturbation. So for small beta, it's just in the paramagnetic phase. And if you take beta to infinity, then you get a cat state. So we have these 2 limited cases, and then the question is what happens in between. Now, if you give me a state, and it has a Z2 symmetry, and you ask me what phase it's in, then what I would do is I would compute the order and disorder parameters. So in 2 plus 1D, I would compute the 2-point correlation functions of charge operators under the Z2 symmetry. And the disorder parameter is the symmetry operator for a patch. So these are the order and disorder parameters, and I would see how they would scale. So in the paramagnetic phase, what we would expect is that the order parameter would decay very quickly as I take these 2 points apart. And then we would expect that the disorder parameter decays with the perimeter of this region. On the other hand, in the ferromagnetic phase, we expect this 2-point correlation function to gain an expectation value order 1, and for the disordered parameter to decay with the area of this region. So it would decay much faster. That's what we would expect for these gap phases. But for this particular model, you can very easily see that the order parameter for this 2-point correlation function is just the spin-spin correlator in the 2 plus 0D classical Ising model. And it has a critical temperature in the classical Ising model. And so this will decay very quickly below this temperature, and it will be order 1 above this temperature. On the other hand, the disorder parameter, you can also very easily compute. You just sandwich this product of x and this disk between your state, the bar and the ket, and then you can see that all of these interactions commute with this symmetry operator in the bulk of your disk and in the exterior of your disk. But the ones near the boundary of the disk, this beta gets flipped to minus beta and it annihilates with this side. So it's like the partition function of 2D Ising here times the partition function of 2D Ising out here, and you deleted the bonds around the perimeter. So you can clearly see that this will decay as the perimeter of this disk. So in this particular model, what we find is that for small beta, less than the 2D classical Ising beta C, the order parameter decays very quickly, as we would expect in the paramagnetic phase. And the disorder parameter has perimeter law. But for beta is greater than beta C, this still has perimeter law. And now this is order 1. So this is an example of a very simple state in which we have this incompatibility show up, where it's not what we would expect for any gapped phase that we know. And this model has been studied extensively, and it's been shown that for betas less than beta C is certainly in the paramagnetic phase. And at beta C, there is a conformal quantum critical point that's Z numerically validated to be Z equals 2.17. And for betas greater than beta C, in a lot of the literature, it was kind of assumed that maybe it's gapped because it has order 1 order parameter, but it wasn't completely clear. So
the conformal is 2 plus 0 dimensional conformal.
Yes, yeah. So equal time correlators. Yeah. Okay, so then when we came across this model, there were 3 possible resolutions. One resolution is maybe in the ferromagnetic phase, you don't need to have area law decay of the disorder parameter. That isn't proved anywhere in the literature, right? That you need to have area law decay of the disorder parameter. So maybe you can still have perimeter law decay, and you can still be in the ferromagnetic phase. Another possible so the other 2 resolutions are what we kind of throw at the problem when we don't really know an answer. So maybe it's the ground state is extensively degenerate, or the other thing is maybe the parent Hamiltonian is actually gapless. So these were the 3 options that we voted on in my office that day. Yeah, so Rahul and Ruben voted for number 2, and Zushi and I voted for number 3. And turns out that Rahul did some preliminary numerics, and if you just do ED, you can clearly see that there's another state that comes down, and it becomes exponentially degenerate with this lowest energy state at beta C. So this is the beta C of the 2 plus 0D classical Ising model. And it's not clear at all that there's any gaplessness up here. So at first we were like, okay, maybe we just don't understand gap phases actually, and it can still have perimeter law decay. And I should mention that this gaplessness is also e to the minus r, not e to the minus r squared. But then if you work hard in DMRG, and Rahul found that it's actually 1 over L squared gapless, that simple parent Hamiltonian that I showed earlier. And you need to get to pretty large system sizes, so this is 4 by 4, 6 by 6, 10 by 10 on the torus. I think Rahul also did these 2 points, but I didn't show them. And what you can show is, for that parent Hamiltonian, for beta goes to infinity, it is indeed extensively degenerate. But we always want to take the thermodynamic limit first before we take beta to, we always want to take L to be much, much larger than any other parameter in the Hamiltonian. So if we do that, then that simple Hamiltonian that I showed earlier is always gapless for betas greater than beta C. And it's 1 over L squared gapless according to these numerical results. And so because we won the bet, then Rahul and Ruben had to buy us sweet potatoes. Okay, so there's a couple things that maybe I should mention before I talk about the low energy states. One thing is, how do we prove area law? In the sense that I mentioned earlier that we expect that in the ferromagnetic phase, we expect that the disorder parameter decays with the area of the patch. And now that we know that this doesn't violate that conjecture, how do we prove that we should have an area law decay of the disorder parameter? One thing you can do is you can take this ansatz. So suppose that your state is finite depth connected to the ferromagnetic fixed point. So it's connected by some finite time evolution of a local Hamiltonian, and this is a Z2 symmetric Hamiltonian to the ferromagnetic fixed point. And then, and what we want to prove is that if this is the case, then the disorder parameter for this patch decays as the area. So with some simple massaging, you can take this expression and you can write it as equal to this commutator of, now this is an operator supported way outside of this patch. So it's the operator supported in the complement of the patch. And it's the commutator of that time-evolved operator with an operator deep inside here. This is a symmetry odd operator inside of your patch. So you can write this. It's not hard to show that these are equal. And now you can use Lie-Robinson bounds, right? So you can show that because this is operator supported way out here, and it's time evolved by something that's finite time, it can only leak with exponential decay inside of this disk. So this commutator with the Zj should decay as the distance, as the radius of this disk. So that's how people usually prove bounds on order disorder parameters. However, the Robinson bounds only give a perimeter law bound. It's always something linear distance. So it can't give you something that decays more strongly, like with area, like what we wanted. So how do you prove something stronger? Well, you can pretty easily show by the same steps as you took to get from this expression to this expression that you can also write it as a huge nested commutator with charged operators all in the bulk of this disk. So now you have this big nested commutator, and the hope is that this big nested commutator is bounded by something that's more tight than the single commutator. And so that's one approach to try to prove that the disorder parameter has a decay with the area in the ferromagnetic phase. And so that's work in progress with Chaoyuan and Andy Lucas. And if you asked me 2 weeks ago, I probably would have said I'm confident in our result and it's rigorous, but my collaborators are very good at poking holes in my proofs. So, but we think we have an idea for how to prove bounds on this big nested commutator that will give you the appropriate bound. So then if that goes true, then truly this state that we originally had for betas greater than beta c can't be adiabatically connected to the ferromagnetic fixed point. I should also mention that this state, if you take the dual Ising version, so you replace the ZZ by just a single Z, and then you gauge the Hamiltonian, so you get this simple model. Certainly for beta it's very small, again you get the deconfined phase of the torque code. And you can very easily see that this N labels the 4 degenerate states on a torus. So it's 1, 2, 3, 4. And there are 4 ground states always for any beta. And they're always degenerate. However, for betas greater than beta c, you can show that these 4 ground states are actually locally distinguishable. And you can pretty easily see that because for beta is very large, this state is just a superposition of all of the closed loops in the sigma z basis, right? So it's all sigma z up, and then you insert loops of sigma z down. And for beta is very large, and that will favor the state that has no loops at all. However, if you're in a non-trivial sector, then you always have a big loop. So that magnetization is mostly obtained from that one big loop that defines your sector. And so, so you can pretty easily see that there should be a total magnetization that should scale as the linear size of your system. That's different between the 4 ground states. And people also study this in numerics as well. And so using those properties of 4 degenerate states that are locally distinguishable, you can also use some lemmas in this paper here to show that this state is not in any gapped family of Hamiltonian. This Hamiltonian is not, but does not belong in a family of gapped Hamiltonians, at least if the original Ising picture, the interactions were all Z2 symmetric. So, and they also computed that the TEE goes from log 2 to 0, and it's always area law for any beta. Okay, so with all that in mind, we think that this top part is probably false. You can't have parameter law, disorder parameter, and still be in the ferromagnetic phase. The second one is not true, except not generic at least. And then the third one is what we find to be true in this case. So this is our main conjecture. So the main conjecture is, given that particular Roxar-Kibelson state, for beta is greater than beta C, any Z2 symmetric parent Hamiltonian, any local Z2 symmetric parent Hamiltonian has to be gapless or have ground state degeneracy of greater than 2. And so what we found is that this is the paramagnetic phase. This is Z equals 2.17, but this is actually Z equals 2 gapless over here. So it's an anomaly-like result, but it's not from any anomalous symmetry. It's just from some constraints that we want on the correlations. And psi of beta looks like a gap ground state. All the connected correlations decay to a constant. This entanglement is pure area law without any logarithmic correction. And this story generalizes to a broad class of models. So, and all these kinds of Roxar-Kibelson type models, or also this kind of model seems to pop up in other places in the study of density matrices and their choice states. So this is...
So when you say gapless, you mean a whole continuum of states?
Yeah.
I see, not just a few states near the ground state.
Yeah, I mean, to be fair, we haven't studied numerically in depth the whole continuum of states, but that's what we hypothesized to be true. Yes?
Is that true in the entire parameter regime that the state is a finite bounded type?
You mean if this is Z equals 2 gapless for this whole region?
No, I mean, for the entire region of beta, is it true that its state is a finite bounded dimension?
Yes.
Then you say when you prove its area law, it's the non-trivial part that one cannot have a lot of distinct subleading terms? Because types always have area law in complement.
Yeah.
Leading terms.
Yes.
So when you say you prove its area law, it's the non-trivial part that you cannot, that you don't have a subleading term?
Well, we didn't necessarily prove that it's area law, but it was already known in the literature that it's area law. But I think the non-trivial part is we see Z equals 2 gaplessness in a lot of 2 plus 1D quantum systems that spontaneously break a continuous symmetry, right? But they also have a logarithmic term, but we don't have that here. Yeah.
So how do you know it's Z equals 2 gapless? Is that from numerics or there's some other argument?
Yeah, so it's probably not Z equals 1 because it doesn't have parallel decay of any correlation functions. And then the Z equals 2 was obtained from the numerics.
I see, okay.
Yeah, I don't know if it has to be Z equals 2, or it could be something else as well.
If I made a subregion which had fractional dimension between 1 and 2,
Okay.
Do you expect that there would be, the distance scale squared, or would it be the boundary?
The boundary.
Right.
Yeah. So yeah, it would be the boundary for this model here, by the same arguments as I showed earlier.
Just want to make sure the spectrum of this model is the same as the correlated model, the deformed correlated model.
Yeah, except there's other degeneracies in the deformed Tor code model from the topological sectors.
That's the only difference. So the Tor model has 4 times the degeneracy of this one.
So in the ferromagnetic beta is greater than beta C, this has a twofold degeneracy split by e to the minus beta times the linear system size. And then in the Tor code one, there's always a fourfold degeneracy no matter what beta is.
That one is due to some kind of non-unitary symmetry and
Yeah, so that's what it was discussed as in the Huxford et al. Paper as like a non-unitary symmetry, but we weren't entirely satisfied with that framework. It is the same, yeah. So if you like gauge this model, it would be exactly that model. So there would be a direct connection.
So you say that context with beta going to beta z is a line of fixed point, or it's controlled by one fixed point?
Yeah, so for this particular model, it seems like it's like a fine-tuned line in the sense that there are like just adding a ZZ kind of field will immediately take you to a gapped phase.
Yeah, well,
yeah.
both have scales on line.
Yes.
So is there anything that I can tell the difference between beta equals to, for example, 3 and beta equals 4?
Yeah, so the coefficient of the perimeter will decay.
Coefficient of the perimeter.
Coefficient of the perimeter is like 2 beta, basically.
Yeah. Okay.
And also, yeah, the order 1 of the order 1 correlations will change.
Yeah, so about the z equal to 2 gaplessness again. So all this equal time correlation function decays exponentially, right, with finite point insertion. Mm-hmm. So, like, how do I think about the excitation? What would be the type of operator that would create an overlap between the ground state and whatever that is going gapless?
Yeah, I'll mention what the low energy excitations look like.
I see.
Yeah. And I should mention that for any gapped ground state, you can also construct z equals to gapless Hamiltonian. So for torque code, the normal torque code, you can also construct a z equals to 1 over L squared gapless Hamiltonian, whose ground state is the normal torque code. But there's another gapped Hamiltonian with the same ground state. So the difference here is that we have a ground state that has z equals to gaplessness, but we don't think there's another gapped Hamiltonian that would have the same ground state, that also has the same degeneracies, et cetera. Okay, so as mentioned, there are low energy states at energy 1 over L squared. And there are, as shown before, beta is greater than beta c. There's one state that comes down and it is exponentially degenerate, but then there's these other states that also descend. And this is the low energy states for this current Hamiltonian, at least, look like thick loops. So what does that mean? If you look at the ZZ correlation between a spin, so this is a 8 by 8 torus, you can see that these two strips are very aligned. And then it goes to anti-aligned at the opposite side. And so this is aligned and this is anti-aligned at the opposite side of the torus. So this is, if you take the torus and you draw like a thick loop on it, and it kind of interpolates between the two. Spin down and spin up. And because you can also check that the ground state is translation invariant, so it's not just the single state, but it's a superposition of like this state and its translates is what we think this is. And so it's like a wave of thick loops on the torus. So why are thick loops special, and why might we expect them to be the low energy states of this Hamiltonian? If we look at the Hamiltonian again, you can see that as beta goes to infinity, you will not want to have spins that are anti-aligned, right? Because if you have spins that are anti-aligned, then this would be very large. So you want to have spins that are aligned. However, as beta goes to infinity, all you really need are for 3 bonds to be aligned. So for any, say, this spin here, you only need these 3 guys to be aligned, and this guy can be anti-aligned. Because if you do that, then this still goes to 0, and the beta goes to infinity. So that means that a configuration like this is bad. So in the beta goes to infinity limit, you actually have many, many, many ground states. You have an extensive number of ground states of this particular Hamiltonian. But this is not one of them, because you can see that this spin has 2 anti-aligned bonds, and this one also has 2 anti-aligned spins, neighbors. But this state is a perfectly fine ground state, right? Because for this state, all of the spins, the nearest neighbors, 3 of the 4 are aligned. So this is an exact ground state of this Hamiltonian in the limit that beta goes to infinity. And so that's one hint that maybe, yeah, these thick loops are preferred. But there are many open questions. So we are not sure if these are universal properties. So for any ground state, you can have many parent Hamiltonians. And that's just one of the parent Hamiltonians. And we seem to have a nice 1 over L squared gaplessness here. But we're not quite sure if that's a universal property. And we also don't know if the ground states look like these thick loops and these thick loop waves in the presence of open boundary conditions. Because if you have open boundary conditions, then the argument that I made previously that those were zero energy states no longer quite work. And we also don't know if there's an explicit Z2 symmetry breaking parent Hamiltonian that's gapped and has this ground state. All of the arguments that I showed previously were assuming that we keep the Z2 symmetry. We also, but yeah, so it's not obvious to us if exists an explicit Z2 symmetry breaking Hamiltonian. There's probably local Hamiltonians that have a threefold degeneracy that are like the 2 ferromagnetic states and the paramagnetic state. So we don't know if our state is adiabatically connected to one of the states in the ground state space of this Hamiltonian. It probably is. We don't see any other signatures of gaplessness besides the long-rangeness of the disorder parameter and the order parameter. So by all other measures, it seems like it's a gapped ground state. And because there's no other signatures of the gaplessness, we don't know if there's actually a direct relation of the Z equals 2 gaplessness to the choice states of the density matrices. So there's many density matrices you can write down whose choice states, like if you take the operator and then write it as a pure state in a double Hilbert space, their choice state demonstrates this incompatibility of order and disorder parameters, but we don't see any other signatures of the gaplessness, so we don't know if that has other implications on the density matrix. And we also don't know if there's any special emergent symmetries. For example, Lifshitz theories have like a U1 symmetry that's shifting the scalar by a constant. There's no like manifest or explicit U1 symmetry in our model. So there's many models that you can cook up that are like Roxar-Kivelson, and they have a U1 symmetry, and they also have the Z equals 2 gaplessness. But we don't have a U1 symmetry. But there might be some emergent symmetries that we don't see very explicitly in the particular model that we have. So there are many kinds of things that we don't quite understand, but hopefully we'll understand them in the future.
Very interesting talk. Questions?
A couple of questions. And so you mentioned the Roxar-Kivelson being Z equals 2, but that's only at a very special point. It's not over generic phase. So you're suggesting something similar over a whole generic phase. Is that right?
Yes.
And in the Roxar-Kivelson context, I remember there was a way to formulate it as a theory with supersymmetry. I'm wondering if your Hamiltonian has a hidden supersymmetry.
That would be interesting. I would have to look at how they found that in Roxar-Kivelson to see if there's.
There are papers on that.
Okay.
Yeah, I think the Roxar-Kivelson point is a special point, but I suppose we require like the Wilson loop has some perimeter law, and the dual boson field has a power law correlation. Probably it will stay there, just like here. So it will remain gapless probably, right?
Gapless as a function of what?
Well, I mean, it just we cannot tune V over T anymore. If we require perimeter law of the gauge field and require the dual boson has like a power law correlation, then we cannot tune V over T.
Correct.
It's like here, right? It's like, so suppose we require the disorder. I know, I mean, then we can tune something else so for example, tune like gradient square phi square, the coefficient of that term, right? We can tune that, So I suspect here it's like tuning that parameter.
Okay.
Yeah, because here actually for any beta, she has the exact wave function, right? There it's the same thing. We can for any k we have a wave function we can write down. So it's a two-dimensional stomac model. Yeah.
So since this wave function corresponds to some 2D StatMech model, I was wondering whether it would make sense to consider some one-dimensional disorder operator which corresponds to that 2D system.
What would you want to, like, you would want to compute the expectation value of product of x and a line or something?
Yeah, x or maybe zz. I'm not sure, but there should be some one-dimensional disorder operator in the original two-dimensional StatMech model, and that, I guess, should be able to distinguish the two phases.
So the 2 plus 0D, classical model also has notion of like disorder operator, and that's obtained by like flipping the bonds for.
At least there is such operator at the critical point. Away from that, I'm using the 2D to 1 plus 1D mapping, although that's not.
Yeah, but that's a quantum 1 plus 1D model, right? So
yeah.
Not quite sure what the relation would be to like spatial 1D operator.
Thanks.
Cal, you briefly mentioned something, but which of these properties, if you think of it from the perspective of the parent Hamiltonian, which of these properties are stable to generic symmetric perturbations?
There are very few things that are stable to generic symmetric perturbations. For generic symmetric perturbations, it generically goes to gapped. It goes from this gapless line to a gapped phase. So all of these things, like the low energy states, they're unstable for beta is greater than beta C.
So even this thick loop excitations, all those.
Yeah, so that was studied numerically. So it was shown that for this particular Hamiltonian, right, the beta equals 0 and then beta C, if you turn on like a ZZ term, then the conformal quantum critical point is immediately turned into a 2 plus 1D ising transition. And then on the ferromagnetic side, it goes into the ferromagnetic gap phase.
Thank you.
So have you checked that like all of the states have 1 over L squared scaling in the z equals 2 phase?
What do you mean by all, like?
Well, like, I mean, like, is it possible that like the first excited state has 1 over L squared scaling, but like not all of them do, so it's not actually scale invariant? Like.
Yeah, it is possible. I think that the technical answer to that is we've only checked the lowest 1 over L squared state. It seems it would be quite weird if there was one state that was 1 over L squared. That would be even weirder than if there was a continuum, I believe. But indeed, we haven't checked for other states.
In the large beta case, where the ground state is a cut state, right? So is it possible to check whether some variational thick loop excitation would still be a gapless excitation? Is it possible to construct this and then verify that in the large beta case? Yeah, so strictly the beta, like for that case, you need to take L e to the minus 2 beta to be much, much less than 1. So you need, if you take the thermodynamic limit first, then these states will never be a zero energy state. However, if you take beta to infinity first, then these will be zero, these thick loop states will be zero energy states. So that's a caveat there. And yeah, so we wanted to, so what these states look like is like a dressed thick loop, right? So it's like you apply the thick loop, but with some dressing on the sides. So that is like a question that we want to see if there's a way to, it's very surprising that you can just like dress the boundary and then it becomes a 1 over L squared gapless state. But we don't currently have a nice analytic way to get that dressing. But yeah, that is something that we want to consider.
Thank you. So statements about autoparameter, so ZZ correlations in your wave function correspond to statements about the 2D Ising model.
Yes.
Right. Are there similar mappings for the disorder parameter? Like, is there a statement you want to make about
Yeah, that would be like if you deleted all the couplings in the perimeter of the region.
Deleted all the couplings?
Yeah, because so it's like the partition function of ising in the bulk and partition function of ising in the exterior divided by the partition of function of ising everywhere. So it's like the free energy, like if you, of that parameter. Is that what you're asking for?
Yeah.
Yeah. That's from the, like, you could just see from computing the expectation value.
Yeah, thanks. Very interesting talk. So maybe I'm a bit confused, but yeah, I think I understood this sick loop argument, but that would give exponentially degenerate ground state, and then there should be infinitely many such states.
Yes.
But in earlier slide, you showed some numerical result, and you found only few exponentially degenerate states. That is just because of the finite size effect? Or?
So there are two exponentially degenerate states that are just like the cat state and the minus cat state. And then the 1 over L square states are the ones that we believe are related to the thick loops.
Oh, okay. So those are high energy states actually you expect to come down eventually for large beta.
Yeah.
Okay, cool. Thank you.
And I guess like people have done lots of numerics on this model, but because the low energy states are these weird thick loop states, so maybe it's hard to see in small system sizes because you need a certain torus size to get a thick loop to begin with.
Yeah, this is equal to 2 states maybe is kind of unstable. But the question is that whether it is a critical point between two more stable states, so maybe between the gap state and a z equal to 1 state. Basically, my question is that if you add a perturbation to your model, can you obtain neighboring state which is either gapped or z became equal to 1?
So there is definitely z equals 1 because I mentioned that the conformal quantum critical point goes from z equals 2.17 to z equals 1. So there is a z equals 1 line.
Above this beta c?
Yeah, so maybe I can, I don't know if you can see.
Yeah, you can.
Okay. But there's something like this. So this line is z equals 1.
Okay.
This is,
where's beta c?
Fair. This is beta c.
Oh, I see.
This is beta equals beta, and then this is some other
vertical line
parameter.
is a certain perturbation.
What?
The vertical line is a certain perturbation.
Yeah.
Okay.
It's like a ZZ coupling perturbation. And so this is a z equals 1 line, z equals 2 line, z equals 2.17.
Okay. Then there's a ferromagnetic state supposed to be gapped.
Yes.
If you go below that line, what happens? If this perturbation becomes negative, what happens?
We don't know.
I see. The reason I ask this question is the following. In our study, this self-dual model in 1 dimension. We also see this z equal 2 states. And there, the z equal 2 state is a critical point between the commensurable phase and the incommensurable phase. So I wonder whether this could be a general feature. Because z equal to 1 critical point, z equal to 2 critical point is kind of strange. But if the other side, so for example, what I try to say is that if the other side is somehow have some incommensurability, then from ferromagnetic to incommensurate state, whether the critical point happened would be z equal to 2 state.
Sorry?
Then I would rather expect higher z at the critical point.
Sorry, what was the statement?
My statement that if this scenario would be realized with some incommensurate critical phase below z equal 2 line, then it's hard to see why that 2.17 that you have at the critical point where z equal 2 line starts would appear.
I guess there could be some other line here, right?
That would lead to higher z.
Yeah.
So the conjecture is that measured incommensurate state, maybe generically is described as a high Z state, if this transition is continuous.
Uh-huh.
Yeah, but here there's no Fermi, but anyway, there's somehow it's similar. Yeah, exactly. Yeah. Oh, I see. So you generate some kind of bosonic Fermi surface.
So the Z equals 2 theory, just the partial T phi square plus gradient square phi square, right? And I actually turning on that term is like turning on like gradient phi square. And changing the sign of that term will naturally generate a wave, incommensurate state, right? So that's probably the case. So this one is the tuning the gradient phi square term to be 0.
Okay.
I see.
Actually, assuming no emergent symmetries like U1, do you expect this gapless phase can be described by Xiaogang's prescription, like 3D Z2 gauge theory? And
yeah, I don't know. It's because this is a Z equal to 2. Z equal to 2 is it's a more complicated. Yeah. So I don't know how to do this Z equal to 2. But however, there's a related question that because the other side of phase is incommensurate, and that means this critical point have emergent U1 symmetry.
Yeah.
That maybe eminent U1 symmetry, because when you have an incommensurate phase, the translation, a lattice translation, will become a continuous symmetry in the low energy effective field theory.
Uh-huh.
Because the incommensurate gave you this non-trivial crystal momentum, which is like a charge of this emergent symmetry. So that's Mesos fit. So maybe this Z equal to critical point would have this emergent some kind of U1 or R symmetry coming from the lattice translation. That's kind of, I don't know whether this could be a general picture. Yeah.
Okay. Yeah, so you're saying that the lattice translation symmetry will become there's a difference though, right? If it's emergent or eminent. So
it's eminent. So there's a lattice translation between eminent symmetry of low energy effective field theory at this Z equal 2 point.
Uh-huh.
So that's also below that for the incommensurate phase. That's also
okay.
And also because it's an emergent U1 symmetry, the incommensurate phase probably is gapless. Below is gapless, above is gap.
Uh-huh. Yeah, it's not obvious to me because usually when there's eminent symmetry, there's a lot that goes into that statement, right? You need to show that all of the operators are disallowed, so it's not obvious to me that it would be an eminent symmetry. But
is an incommensurate phase.
Yes.
Below this line is incommensurate, then that statement looks more natural.
I see. Yeah, that would be interesting to make more concrete.
I was wondering, so in Roxar-Kivelson type models, oftentimes putting these models on different lattices will give you different behavior around the Roxar-Kivelson point, whether it's part of a phase or a critical point or something like that. I was wondering, for this model, if you put it on other lattices, is there any reason to expect that this gaplessness would be preserved, would turn into a phase, would disappear, something like that?
Yeah, so actually, if you put this on not a square lattice, but like a hexagonal lattice, then there's nothing special about thick loops for this particular Hamiltonian. And the reason is if you are on a hexagonal lattice, then you have this state where if you have like all up here and all down here, you can show that this also is a zero energy state in the beta goes to infinity. And and there's also like a difference, like this PEFS is weakly non-injective on the square lattice, but not on the hexagonal lattice. So indeed, there is interplay with the particular lattice. So we don't actually know what the low energy states look like for the hexagonal lattice.
But in the hexagonal lattice, it's still Z equals 2 gapless? Or
we would expect so, because you still have this, the order parameters and the disorder parameters are still
still behaves the same way.
It stays the same. So we would expect so, but in terms of what the states look like, it's not obvious.
Thanks.
Yeah, I was just going to ask, this is related to Tenko and Xiaogang's comments earlier. So the z equals 2 theory, although the gap scales as 1 over L squared, it doesn't seem to have a local field theory description, right? Because your excitations are these highly non-local objects. So it's not clear to me if intuition from like gradient square phi squared type Lagrangian should apply in this scenario. So I was wondering if you have some kind of effective field theory description to capture the gapless states, or is it you only know that the gap scales as 1 over L squared?
Yeah, we don't have an effective field theory, although one thing to note is on the hexagonal lattice, there are local operators, right? The spin flip for this hexagon is a 0 energy state for beta goes to infinity. So it might give you a low energy state. So it's possible that on this different lattice, you don't have these non-local operators that create your low energy states. And that might give, yeah, but in terms of like an effective field theory, you don't have a local effective field theory directly derived for this.
The remaining questions for dinner. Let's thank Carolyn again.